Okay, God bless we all. Okay, the last video we stopped up to the measurements. We have completed the measurements. In this video, we will continue the dimensions. It's also under unit 1. It's dimensions. So what are dimensions? In physics, dimensions are used to describe physical quantity by expressing it in terms of basic units. Every physical quantity, whether simple or complex, can be broken down into combination of these base quantities. Okay, the dimensions in the system of SI units, as we already know, the mass, length, time, electric current, thermodynamic temperature, the luminous intensity, and the amount of substances are the basic units, basic SI units. The other quantities such as energy and the accelerations, likewise, those we can derive from the basic SI units are called derived SI units or derived units. The symbolic expressions which show the relation of a physical quantity to basic units. Physical quantity to basic units is called its dimension. In studying mechanics and properties of matter, mostly used dimensions are mass. We are using capital M as dimension, and the length using the dimension as capital L, and for time we are using the dimension as capital T. Also, there are dimensions for the other quantities like temperature, we are using a theta, the electric current, we are using a capital I. The way of finding the dimensions of several physical quantities we meet in mechanics are given below. For example, if you take a physical quantity of area, the basic relation or the definition is length into breadth. You may know, that the length and breadth are in the same dimension. So what we are doing here, L into L. So the dimension of area is now becoming L squared. L squared. Similarly, the volume, the basic relations or the definition is length into breadth into height. So the dimension of the volume is now L into, so length is L and the breadth also dimension is L and the height also dimension is L. So the dimension of volume is now L cube, L to the power 3. Similarly, the density is the relation of the basic relation of the density, or the definition of the density is mass over volume. Mass over volume. So in that case, the dimension of mass is, what we have studied is M over volume is L cube. L cube. So the dimension of the dimension of the density is now is ml minus 3. Similarly, the velocity is the displacement over time. It means the displacement is L dimension and the time is capital T. So the dimension of the velocity is LT minus 1. Likewise, the acceleration velocity, you may know, what is velocity? Velocity is LT minus 1 and over time is LT minus 2. Over time, LT minus 1 over T is equal to LT minus 2 is the dimension of acceleration. Then force. The force is equal to the relationship of basic relation or the definition of force is mass into acceleration. The definition, the dimension of mass is m into the acceleration is LT minus 2. LT minus 2. So the derived dimension of force is ml t minus 2. Not this one. ml t minus 2. ml t minus 2. Okay. The next is quantities without units such as refractive index, coefficient of friction have no dimensions. No dimensions because it doesn't have units. It doesn't have units. There are quantities with units but without dimensions also there. There are quantities with units but without dimensions are there. But in the refractive index, the coefficient of frictions are unitless. So it also no dimensions. But there are some quantities with units but without dimensions. Example, plane angle and solid angle. Correct. Several uses of dimensions are given below. Dimensions we can use first, number one, to check the correctness of a given relations among physical quantities. To check the correctness of a given relation among physical quantities. The second one is to derive a relation among physical quantities. To derive a relation among physical quantities. Okay, checking the correctness of an equation using dimensions. How several physical quantities are related to one another is expressed mathematically by a physical equation. If the equation is correct, the dimension of its both sides should be equal. So underline the word. You have to remember that if the dimension its both sides should be equal if the equation is correct. If the equation has several terms, the dimension of all separate terms should be the same. So what is that meaning is, let's say that A is equal to BC plus D over E. It means dimension of A, okay, dimension of A should be equal to dimension of BC is equal to dimension of D over E. This is what they are mentioning here. If the equation is connecting physical quantities, then A is equal to BC, then dimension of A is equal to dimension of BC is equal to dimension of DE. This concept when we using to check the correctness of the equation. Okay, let's see worked examples. If an object that travels along a straight line with an interval, if an object that travels along a straight lines with an initial velocity u and a uniform acceleration a for a time t and attains a final velocity v, the displacement experienced by its s equation related to motions are given below. What's Okay, there's a linear motion. Okay, an object is starting with an initial velocity u and with an acceleration of this travel, it's a uniform acceleration for at a time t. Let's say this is at a time is equal to 0, and when the time is t is equal to t, the object is reaching the final velocity is v. Okay, this displacement is s. This displacement is s. Okay, this is the simple illustration of that sentence. Check these equations are correct or not. Okay, the first equation is the final velocity is equal to initial velocity plus product of or multiplication of acceleration into time. So we will check this equation first, and then the second equation is explaining that s is equal to ut plus half at square. And the third equation is telling that v squared is u squared plus 2as. And the fourth one is s is equal to v plus u over 2, means it's what? It's average velocity. It's what? Average velocity into time. Average velocity into time is the displacement. The fourth equation is this one. So we will check these all four equations. The correctness of these equations are correct or not by using the dimensions. What is the concept? The concept is if the equation is correct, the dimension of its both sides should be equal. And also, if the equation have several terms, the equation has several terms, all separate terms should be the same dimensions. All should have the same dimensions. Okay. So using these two concepts, we will check the correctness of the given equations under this. Okay. Problem 1, checking the equation is, first equation is v is equal to u plus at, where the v is the final velocity, u is the initial velocity, and the a is the uniform acceleration, and the t is the time taken for this travel. Let's say, already we know that velocity is what? Displacement over time. The dimension of the velocity is Lt minus 1. Lt minus 1. Okay, similarly, the dimension of u also what? It is Lt minus 1. Also Lt minus 1. So these two components dimensions are okay. Now we have to check the dimension of a into t. So dimension of a into t is a. The acceleration's dimension is Lt minus 1 over t, that is Lt minus 2. The time, dimension of time is capital T. So now the dimension of AT is equal to LT minus 1. It means the LHS is what? The dimension of LHS is LT minus 1. And finally, the dimension of each component of U also LT minus 1. And also, what is that? The component AT also dimension is LT minus 1. It means each of these components are equal, and also left hand side dimension is equal to right hand side. So LHS is equal to RHS. Hence, the given equation is correct. Okay, we will check the next one. In the equation, second equation, it is mentioned S is equal to ut plus half at square. This is the given equation in the second equation. Okay. Let's say the dimension of S is what? Length. The length of length dimension is L. Okay. Length dimension is L. Okay. Now we will check each of these should be equal to dimension L. Each of the component should be equal to dimension L. Otherwise, it is wrong. Okay. Let's check ut. The u is the dimension of u. Initial velocity is Lt minus 1. And the multiplication of time. So the dimension of time is capital T. So ultimately, the dimension of ut is capital L. Capital L. Similarly, we will check half. So numbers doesn't have unit dimensions. So we will take at squared only. So a is acceleration. The acceleration unit is dimension is Lt minus 2. And time squared, t squared. So it means t into t squared. So dimension is t squared. So Lt minus 2 into t squared. So ultimately, the dimension of at squared is also L. So the dimension of S is equal to dimension of ut is equal to dimension of at squared. Hence, LHS, dimension of LHS is equal to dimension of RHS. Dimension of RHS. Hence, the equation is dimensionally correct. Hence, the equation is dimensionally correct. The previous equation is at squared, means S is equal to ut plus half at squared. But this equation is no at squared. It is no at squared. It is just half at. For the purpose of checking, we will check this equation is correct or not by using the dimension. Okay. Let's say the S is the displacement, as like that earlier. The initial velocity is u, a is acceleration, time is t. So the solution of ut is equal to L. Is it okay? That's okay. That's okay. So then we will check the at dimension of at. At is Lt minus 2 and the t is t. So now it is Lt minus 1. So this is the ut, dimension of ut. It is, dimension of ut, it is not equal to dimension of at. So what's happening here? L, we have to equate the dimension of ut, t minus 1. So to remove this t minus 1, we have to multiply by the dimension of t. Then it will become the dimension of L. So we have to multiply this unit by t. It means at should be multiplied by t. Then the equation is at squared. So the correct equation is what? S is equal to S is equal to ut plus half at squared. So this is the correct equations, and the at squared dimension is finally L. So dimensionally, this equation is correct. So this is a given equation. It's wrong. It's wrong equation by the checking of dimensions. Okay. Now in the equation, V is equal to U squared plus 2AS. So dimension of V squared is equal to Lt minus 1 into whole squared. This is L squared into T minus 2. Similarly, U squared also Lt squared minus T minus 2. So these two are equal. These two are equal. So we will check that AS, dimension of AS. If it is okay, then this is all the component of these equations are dimensionally correct. Then total equation should be dimensionally correct. Okay, let's say A, the acceleration, it is, we know, LT minus 2. So into S is what? A is what? A is LT minus 2 into S is L. It means, so I think it's wrong. We will check. A is LT minus 2 and the dimension of S is L. So the equation is L squared into T minus 2. T minus 2. T minus 2. So it is equal to the dimension of V squared and U squared. So dimension of both sides of the equation is the same and all terms have the same dimensions. Hence, equations 3 is dimensionally correct. Similarly, we will check that from the equation 4 is equal to S is equal to V plus U over 2 into T. It means V plus U over 2 is average velocity. So another important property of dimensional analysis can be introduced. Another important property of dimensional analysis can be introduced. If there is a term in an equation expressing a sum or difference of two quantities, in the term which sum or difference should be the same dimensions, that is, dimension of U and V should be equal. Dimension of V and same like. So if you same like the previous concept, if you expand this equation, it's supposed to be how? V T over Vt over 2 plus Ut over 2 means what? These equations and these dimensions should be equal to these dimensions. Each and every dimension should be equal. Same things he is telling now. The dimension of U and V are same. So dimension of S is equal to now L. So the Vt and Ut is equal to U. The velocity dimension is LT minus 1 into T. It's finally the dimension of Vt and Ut is L. Hence, the dimension of both sides of the equation is the same and all the terms have the same dimensions. Hence, equation 4 is dimensionally correct. Dimensionally correct. Okay, the final one is derivation of equation by the method of dimensional analysis. Derivation of equation by the method of dimensional analysis. Okay. Suppose we want to develop an equation for the periodic time capital T of simple pendulum. First, we have to identify experimentally or logically the quantities related to the periodic time. So here we can assume that the periodic time depends on the following quantities. Okay, let's say if you want to develop an equation of the periodic time T of the small pendulum, first we have to know the identify the experimentally or logically the quantities related to the periodic time. Periodic time. Here we can assume that the periodic time of depends on the following quantities. For an example, let's say the pendulum, we'll draw a pendulum here. Okay, this is the pendulum now. This time is depend on what? This definitely depend on this mass. Depend on this mass means mass of the pendulum bob. This is the bob of the pendulum. So mass of the pendulum bob. If the pendulum mass is high, what happen? It will the oscillation period will be short and it will not much oscillate. If the pendulum small mass means it will oscillate easily. So the time taken for the oscillation will be high than the mass. So the time of the pendulum periodic time, it's depend on the mass. Then the second one is length of the pendulum. This is called L. This also, what will happen? If the shorter L, what happen? It will oscillate. The time will be high. So we will, why it means it will in a shorter period, it will oscillate very higher range. If we extend this L to some far here, what happen? The acceleration will be short. Acceleration will be short distance. So the time taken for that distance will be very lower than the short length pendulum length. So third one is gravitational acceleration. Gravitational acceleration also give an impact of this periodic time. So using this three quantities which are logically related to the periodic time, we will derive equation for the periodic time of the pendulum dimensionally. Okay. So since we have no idea about the correct relation among the quantities, we can write just, okay, we will write T is proportional to mx. Actually, before we don't know the correct relationship between the T and the related quantities, logically related quantities. So we will write capital T. That means periodic time of a pendulum is proportional to M and L into G. So we don't know the exact relations. That's why we propose M to the power X and L to the power Y and G to the power Z, or G to the power Z. So finally, to remove this proportional symbol, we multiply this one is by a constant. Then it is becoming T is equal to K into M into X to the power relation into L into Y to the power, means that's the relation of with the T and the gravitational acceleration. The relation is Z. Okay. So this is the equation. Now we have derived the proportionally constant without a dimension. Okay. So now applying the dimension to both sides of the equation. So now it's coming. Now we know this one is constant. This one is constant. So constant, it means it doesn't have dimension. So we will equate the dimension of both sides. So applying the dimension of the both side equation now, so T is M into X, that is mass. So M is here, capital M, dimension of mass is equal to capital M. The length dimension is L, so L into Y, and G is LT acceleration, that is LT minus 2, LT minus 2 into the power Z. So we are equating the time is capital T of the pendulum periodic time, capital T dimension is equal to mx into L into the power Y into LT minus 2 into the power Z. So by what we are doing now here, so capital M X into capital L Y into L into Z and into T to the power minus 2Z. T to the power minus 2Z. So we are grouping this one, M into the X and L Y plus Z and T minus 2 to the power Z. So equating the indices of M. Indices of M. So if an equation is equal, means the indices should be equal. So the indices of m is x in the right hand side, but in the left hand side there is no indices of m, or there is no dimension of m. Hence it should be equal. So mx should be equal to 1. That is the case. X is equal to what? Is 0. X is equal to 0. So equating the indices of L means y plus z also 0. Y plus z also 0. Then equating the indices of t, what happened? Minus 2z is equal to 1. It means z is equal to minus half. That is equal to minus half. So the relations among the quantities can be written as T is equal to K is constant, M is equal to what? 0, and L into half into G into minus half. G into minus half. So we can write here is equal to K into L over G. L over G. So now you see, by logically, as I explained earlier, by logically there is a possibility, or there is a relative quantity which will affect the periodic time of the pendulum. But after deriving this equation, the pendulum bob's mass, it does not depend on the time. Does not depend on the time. It's depend on the L and G only. The value of constant K cannot be found by dimensional analysis. By dimensional analysis, we cannot find this one. By experiment, it can be T in one. We can tabulate the T in one table. So we can make a experiment like this for a pendulum. The pendulum. Okay. For different L, for a different L, for L1. So let's say L1, we have to monitor, or we have to check the read the time T, periodic time T. Okay. Then for L2, what we have to do? We have to observe the periodic time T2. And then for L3, we have to observe time T3. And likewise, L4, we have to observe time, it's T4. And L5, also we have to observe time is T5. This equation is, seems this is in the y-axis. So K is, we can say M. So finally, what we have to do, L over G. So you have studied in O level. So the G value you know. So what do we have to do? L over G value. So find the L1 over G, L2 over G, L3 over G, and L4 over G, and L5 over G. Now this one is tabled, and take a root of this all. Root of this all. Then this is the value of L1 over G, root L2 over G. Likewise, you can fill this all. After tabulating this, what is this? This is the X value. So using these records, observations, and data, you can plot a graph. So T is here. This is root L over G. So this gradient is theta. So then tan theta is equal to what? It's K. So by experiment, we can find the K here to derive the full formula. But dimensionally, we cannot determine the constant K. So by dimensionally, the derived formula is equal to what? T is equal to K into root L over G. Okay. Similarly, you can we can see that F is equal to when a stone is tied to a string and it's moved in a circle in a horizontal plane. We can assume that the tension F gained by the string depend on the mass of the stone, speed V of the stone, and the radius R of the circle in which it moves. Since we have no idea about the correct relations among the quantities, we can write what we can write. So what is saying? Mg, it is surrounding a radius R, and the speed is V. V, the stone, and the radius is R. Okay. So this force, what is telling, when it is rounding, the force is proportional to what? The M, that's we don't know the relationship. So we will assume as X. So the relationship of V and the force also we don't know. So we assume as Y, and the relationship of radius and the F also we don't know. So we will assume it is Z. Okay. So to remove this proportional symbol, we will multiply by a constant, then the appropriate constant values, let's say K, then the equation is equal to F is equal to K into mx into V y to the power into r to the power Z. So by equating this LHS and RHS, so we can get MLT minus 2 is the dimension of force, and the dimension of M is m to the power x, and the velocity is LT minus 1. So the V to the power y dimension is LT minus y into the power y, L to the power minus 1 into the power y. So R is length actually. So the dimension is L to the power Z. Okay. So this one is MLT minus 2. Now by grouping this one, M to the power x, L into y plus Z, and T to the power minus y. Equating the indices of M, okay, this side is 1 is equal to x. So x is equal to 1. Equating the indices of L, y plus Z is equal to 1. So we know already y plus Z is equal to 1. Okay. So equating of indices of T, what happened? Minus y is equal to minus 2. So y is 2. So representing all these, x is equal to 1, y is equal to 2, and z is equal to minus 1. So the correct equation is now F is equal to, we cannot find the K value by dimensionally. So M into y is what? V squared, MB squared into Z is what? R. So MB squared over R. So F is equal to K into MB squared over R. This is the derived formula of the tension in the string F of a stone rounding with the radius of R. With the radius of R with the velocity of V. Okay. Yes. So now we have completed all measurements and the dimensions. In the next video, we will see the past paper questions. Thank you very much. Good luck.